Yeah, so hello everyone. So title of our paper is CORMS, a GitHub and Gerrit based hybrid code review recommendation approach for modern code review. And the authors of these papers are me, Prahar Pandya and Saurabh Tiwari. So this is the outline. So we'll first go through the software code reviews, the code review recommendation problem, motivation, the proposed approach, CORMS, and result and conclusions. So basically, software code review refers to a manual assessment of a source code that identifies a defect and some quality problems like coding rule violations. And nowadays, these reviews are assisted with automated tools, and this review process is known as MCR, Modern Code Review. The figure shows the working of MCR. So in the first preparation step, the authors prepares the change metadata. Next, appropriate reviewers are selected, and this selected reviewer receives a notification to review the change. In code checking, the reviewer individually performs the code checking. Next, they may also interact with the authors or other reviewers. And finally, this reviewer make the final decision, which can be accept, rework, or reject. So, recommending reviewers is the most common support in MCR. It helps the author to select the reviewers, and most of this technique uses the review history to build the recommendation. And but issue arise when inappropriate reviewers get assigned to the reviews, which cause the delay in the review process and also affect the quality of the product. This figure is taken from Android project of Gerrit open source platform. It describes the core review request carried out recently in March 2022. So here we can observe that the author X added a reviewer C, but he was not the actual reviewer for this repository. So he added two more reviewers and removed himself as a reviewer. So finally, the correct reviewer reviewed the code change, but the correct reviewers could be assigned to the review request automatically without any delay in an ideal scenario, but it is not the common case at the moment. So another figure is taken from the Better Scientific Software project of GitHub, which describes the core review request carried out in June 2021. So here author X added requested a review from reviewer P, and after a few days, he reminded author X to reviewed his code. Still, he didn't get any reply. So he posted comment asking if there anyone that has time to review the code. And finally, one reviewer approved the change. And we can notice that how inappropriate reviewer selection delays the entire code review process. So we have summarized the well-known existing core review recommendation technique based on different aspects. So from table 1, we can see that the most of this technique were tested for a smaller number of projects, and also they are based on only one OSS platform, either GitHub or Gerrit. From table 2, we can see that some of the features like authors, sub-projects have never been used before. So we were more interested to figure out the impact of these new features on prediction of reviewers. So for analysis purpose, we used the Gerrit Search API, where we provided different settings for sub-projects and authors. So table 3 compares the two pull requests of the Gerrit OpenStack Python neutral client project. The first pull request is created for updating constraint file, while another one was created for updating Git review file. So here we can observe that both of these pull requests contain the same authors and reviewers. Now table 4 compares the three pull requests of Gerrit OpenStack Puppet Swift project. So from subject field, we can notice that the goal of all these pull requests are same for removing the three polar jobs. We can observe that all these pull requests contain the same authors and at least one common reviewer. But there are so many such code review requests. Finally, we made the implication from this observation, which helped us propose a new algorithm like the textual content in the subject field give the extra information about the change and are good indicators to recommend the suitable reviewers. The project or sub-project information can also help the help recommending appropriate reviewers. Also, similar reviewers can review the review request from the same author as they know each other because of their past collaborations. So Finally, we proposed a new algorithm CORMS, which is core review recommendation based on machine learning and similarity analysis. And it supports both GitHub and Gerrit OSS platform. And it includes 5 features: authors, project, sub-project, subject of the change, reviewer activeness, and file paths. So figure shows the architecture of CORMS. It first collects and pre-processes the data. After that, it passes information to the similarity and SVM model. The CORMS controller then combines the result of both the models and filters the inactive reviewers. So we created different multi-threaded review mining algorithms to mine the data from the Gerrit and GitHub chronologically. So we selected a total of 20 projects from GitHub and Gerrit. So the table shows the statistics of the collected data. Now, the feature extraction includes the selection of only important features. Data cleaning includes the removal of unwanted reviews and boards. So generally, the reviewers data may also include boards, and these boards checks the code compilation, where code passes all the test cases and performs without any issues. So this board can be identified by building the workload dictionary and by analyzing the highest reviewer workload. Then the natural language processing step include lowering the cases, removal of punctuation, removal of stop words, stream lemmatization, and the removal of common words, which we identify by building a most common words dictionary for all the projects. So we use TF-IDF vectorizer to transform the resulting string into numeric vectors. Finally, we split the data into 2 parts: train reviews and new reviews. So the algorithm describes the working of similarity model used in the CORMS. The input of this algorithm includes the new review and all the train reviews. It compares the new review with all the given train reviews by computing the similarities of file path, subject, sub-project, and author features. Using our 4-string comparison technique, it then combines the review similarity score using normalization technique and propagates this score to each reviewer. So the output of this algorithm is sorted list of reviewers. The table here shows the working of all these 4-string comparison technique, like how they generate scores based on comparison of 2 strings. To predict the reviewers based on the vectorized content of subject, we used ensemble modeling by testing the performance of 4 machine learning algorithms over 20 projects. So these algorithms are Naive-Bayes, SVM, random forest, and KNN. So overall, we observed that the best accuracy is in SVM model, and thus we selected that SVM model for the CORMS. So finally, the last algorithm describes the working of CORMS controller. The input of this algorithm is the new reviews and all the train reviews. It builds the reviewer dictionary, reviewer activeness dictionary using the last reviewed date feature. Then it calls the similarity and SVM models for prediction. And after that, it merges and normalizes the result for both the models and removes the inactive reviewer who reviewed 12 months ago. So we have used the top K accuracy and mean reciprocal rank to evaluate the performance of CORMS. In this paper, we have answered 2 research questions, like how efficient is the CORMS in recommending reviewers for reviewing the code, and what is the performance of CORMS in comparison with the state of our Finder, and how much improvement CORMS gain with each newly added feature over Finder. So the figure shows the accuracy comparison between CORMS and Finder. Inside each accuracies, the first column includes the accuracies of CORMS. The second column shows the accuracies of Finder. Third column shows the percentage improvement of CORMS over Finder. The highest improvement of, so we observe highest improvement of about 200% in the Eclipse project. The Finder used a border count combination method for score propagation. The figure shows percentage improvement of CORMS accuracy with the normalization technique and border count combination. So we can observe that the normalization performs better than the border count. The Finder contains only one file path feature. The figure measures the accuracy gain for each newly added feature over file path. So when we added SVM model to the Finder, we observed that nearly around 8% average gain for all the 20 projects. So similarly, when we added the sub projects and author features to the file path, we observed significant improvement in accuracies of similarity model with respect to the Finder. In CORMS, we solved the retired reviewer issues and the issue with the newly created file. We also optimized the accuracies and carried out larger testing in both Gerrit and GitHub to analyze whether CORMS recommend a wider range of reviewers. So we carried out small testing also on the five projects as shown in the table. We observed that the CORM predicts a wider range of reviewers for all the projects. So our dataset containing 34 projects is also publicly available in the Figshare. And in future, we plan to conduct empirical studies with the developers to test the effectiveness of CORMS in practice. So to conclude, we have investigated the current reviewer recommendation issues, and then we have investigated more set of features that can impact the reviewer recommendation and were missing in the existing studies. After that, we proposed a hybrid core reviewer recommendation approach CORMS and conducted detailed analysis on widely used 20 projects of both GitHub and Gerrit. So then we compared our result with the state-of-art Finder, and in the future, it's interesting to add extension for solving the workload issues and the effect of social collaboration with between developers. So these are the references. Yes, thank you everyone.